In this discussion video, we will do some infinite limit examples involving the square root of some stuff. So these are from worksheet 4, problems number 7, part E and F, these two limits here. And I want to first give you 8 minutes combined to try these two problems. So pause the video in 4, 3, 2, 1, pause it, and try these for 8 total minutes. All right, so hopefully you did that. Hopefully you paused it and tried it for about 8 minutes. Let's talk about it. So for E, I have this infinite limit, and I could start it off by just plugging in. I could plug in and see what happens. If I do that, I'll get the square root of 1 plus infinity, which is infinity, square root of infinity. And then I have minus infinity over, on the bottom, we'll get infinity plus 1. So square root of infinity is infinity. So we get that minus infinity over infinity plus 1 is infinity. And on the numerator, infinity minus infinity, this is an indeterminate form. And as a result, I'm going to need to simplify this somehow. And I want to show how to do this in 2 ways. So method 1 is going to be to do it by factoring. I also want to do this for practice without using any shortcuts. So first method, I'm going to do it by factoring. Okay, so we have the limit as x approaches infinity of 1 plus, or actually, sorry, let's just go straight into the factoring. From within the square root, let's take out the highest power of x, which is x squared, and that'll leave me with 1 over x squared plus 1, that being square rooted, minus x. All over on the bottom, I can factor out an x, and that'll leave me with 1 plus 1 over x. Okay, so this equals the limit as x approaches infinity. Now, that square root I can split up to be the square root of x squared times the square root of 1 over x squared plus x, and then minus that x on the outside, over x times 1 over 1 plus x. So as we've seen in lecture, the square root of x squared equals the absolute value of x. And I can think of absolute value of x as a piecewise function. It equals x if the x is greater than or equal to 0. So when the inside is non-negative, I can just drop the absolute value and write x. If the inside is negative, if x is less than 0, then I can't just write x because this would now be a negative number. I need to make sure it's non-negative, so I stick a negative in front of it. Okay, so I want to use that idea. We're going to have the limit as x approaches infinity, and the square root of x squared that I have in this numerator is going to be absolute value of x, times the square root of 1 over x squared plus 1 minus that x over x times 1 plus 1 over x. And now if we use this piecewise function stuff, because x is going to infinity, that means x is greater than 0. And if x is greater than 0, that means the absolute value of x will be equal to just x, because the x is already non-negative. So this absolute value of x, I can replace it with just x. And now I see an x here and an x here, so I can factor them to get the limit as x goes to infinity, factor out that x, and that'll leave us with the square root of 1 over x squared plus 1 minus 1 over, on the denominator, x times 1 over 1 plus x. Now I can cancel those x's that I factored out. And now let's try plugging in. So this gives me the square root of 1 over infinity is getting close to 0, and then plus that 1, minus the 1 outside. And then on the denominator, I'll have the 1 plus 1 over infinity is getting close to 0. Okay, so square root of 1 is 1. So on the numerator, I get 0. On the denominator, I get 1. And 0 over 1 is 0. And that's my answer. So we were able to do this by factoring, identifying the highest power of x on the top, the highest power of x on the bottom, factoring, simplifying, something canceled, and then we were able to plug in and evaluate our limit. So let's do this one other way. So method 2 is going to be to do this. If I look back to the original problem for some motivation here in part E, on the numerator I have the square root of some stuff and then minus a number. That makes me think of conjugate. And that is what method 2 is going to be. Let's try to do this using the conjugate and see if it works. And if it does work, which one's more efficient? Which one gets the job done more quickly here? So I have the limit as x approaches infinity of root x squared plus 1 minus x over x plus 1. So let's multiply this by the conjugate on the top and the bottom. So the conjugate would be the square root of x squared plus 1 and plus x. Whatever I multiply by on the top, I got to multiply by on the bottom. So root x squared plus 1 plus x down here as well. Okay, so now if I multiply, we get the limit as x goes to infinity. So on the top, that's where multiplying by the conjugate helps. And I'll get this first term, the square root term, being squared. And that'll get rid of the square root. So I'll get x squared plus 1. And then we'll get minus the next term, that x being squared, x squared. All over on the bottom, I'm not going to distribute it out. I'm going to keep it as x plus 1 times the square root of x squared plus 1 plus x. Because as we've seen before, the conjugate specifically was helpful for the numerator. And as we've pointed out previously in examples, where that conjugate specifically wasn't helpful, in this case, we multiplied on the conjugate for the numerator, not for the denominator. So on the denominator, it's better not to distribute things out because it'll just make it harder to see if things cancel later. It's better to keep it factored to identify if things cancel later. Okay, so, well, numerator, I can cancel these x squareds. And from there, I actually don't even need any cancellation. The numerator is very simple. It's just 1. Let's try plugging in now. I get 1 over infinity plus 1, and then I get the square root of infinity plus infinity. So this overall is going to be 1 over infinity plus 1 is infinity, and then the square root of infinity plus infinity is definitely infinity. So the whole denominator is just an infinity times an infinity, which is infinity, and 1 over infinity is getting close to 0. And that's the same answer that we got using method 1. Okay, so key things that I want to point out about this is it is helpful to see multiple methods for doing a problem. Multiple methods. So one of the reasons is this lets us assess which of the methods is most efficient. And for this particular problem, doing it by the conjugate I think was more efficient. It was quicker. That won't always be the case. There might be some problems where factoring is more quicker. And the other reason is that this is one of the big benefits of doing group work. It gives you more opportunities to see multiple methods, multiple approaches. So I would encourage you to utilize resources like our peer study group sign-up sheet, as well as the SLC tutoring drop-in virtual space as places for you to work in groups with each other. All right, let's look at part B now, or I guess this is part F of this example. All right, and for that one, I also want to do this in 2 ways. Let's do this first by factoring, and then we'll also do it using the conjugate. It's a really similar expression, except x was just going to negative infinity. All right, so recall we had the limit as x approaches negative infinity, square root of x squared plus 1 minus x over x plus 1. And let's go ahead and factor to get the limit as x goes to negative infinity. If I factored x squared out of this root term and split it up already, I'll get root x squared times the square root of 1 plus 1 over x squared, and then minus the x over, let's factor an x out of the bottom to get x times 1 plus 1 over x. All right, square root of x squared, we know that that's going to be the absolute value of x. And because x is going to negative infinity, that means x is less than 0. And as a result, the absolute value of x, when I get rid of the absolute value, I can't just write x because x is negative and the output of an absolute value can't be negative. So I need to put another negative in front of it to make sure that output is non-negative. All right, so we get the limit as x approaches negative infinity, but the absolute value of x simplifies to negative x now, times the square root of 1 plus 1 over x squared minus x over x times 1 over 1 plus x. Now we see that this x, there's an x here and there's an x here, so we can factor. So this gives us the limit as x approaches negative infinity. In fact, I can even factor out a negative x. Factor out a negative x, and that'll leave us with root 1 plus 1 over x squared, and then plus 1 over x times 1 over 1 plus x. All right, so now the x's cancel. And if we plug in, we still have this negative in front. Negative in the parentheses, we'll get root 1 plus 0, and then plus 1 over, on the denominator, I'll get 1, and then plus 0. And this simplifies to, let's see, we have negative, and then 1 plus 1 inside the parentheses, that's negative 2. Negative 2 over 1, which is negative 2. And that's our answer. Let's now do this using our other method, using the conjugate. So method 2, what does it look like if we do the conjugate? And will that be better here? Method 2 is conjugate. All right, so let's write the original question. The limit as x goes to negative infinity, root x squared plus 1 minus x over x plus 1. And let's multiply the top and the bottom by the conjugate of this term on the numerator, root x squared plus 1 plus x over, and then over square root of x squared plus 1 plus x. All right, so when we multiply, we get the limit as x approaches negative infinity. And we've already seen what multiplying by the conjugate gives us on the numerator. It gives us x squared plus 1 minus x squared, because we saw the exact same multiplication in the previous question. That one was just the limit as x goes to positive infinity. And on the bottom, like before, let's keep it undistributed. So keep it as x plus 1 times root x squared plus 1 plus x. So now we see that these x squareds cancel. And after we cancel them, if we try to now plug in, we are left with a 1 on the top. On the bottom, we will have negative infinity plus 1, which is negative infinity. And then times, we'll get the square root of negative infinity squared will be positive infinity. And even after we add 1 and then square root it, it'll still just be infinity. And then plugging it into plus x, we'll get minus infinity. But this infinity minus infinity, this is indeterminate. So we're not at a point where we could just plug in and get the answer. So when we see an indeterminate form, that means simplify. Okay, so if I kind of go back to this step before I plugged in and think about, well, what could we do to simplify this? One is, at this point, we could say, what if we now factor the highest power of x from the top and from the bottom? So what if we now factor the highest power of x? That's one strategy. And we may not see this yet, but if we kind of go down this route a little bit, we will end up with another indeterminate form. So it turns out this won't be the most helpful thing. And we'd kind of have to do it to know. The other option would be to see that on the bottom, I have this square root of something and then plus something. So I could think, what if I just conjugate this again, but conjugate by the thing that I have on the bottom? If you do that, it'll turn out that we end up going back to where we started. And that we definitely don't like. So I'll put a sad face there. So overall, for this second example, as x went to negative infinity, in this particular problem, it turned out that factoring got the job done, but multiplying by the conjugate didn't. It led us to more of a dead end. So we've seen an example now where in lecture, where this first method, factoring the highest power, wasn't helpful, but multiplying by the conjugate was helpful. And we've seen an example in discussion where multiplying by the conjugate wasn't helpful, but factoring the highest power out was helpful. And the moral there is, sometimes you just have to try a method to see if it's going to work or not. And there isn't always kind of a surefire way to tell, like, well, which method works in which situation. It comes by just trying, and if it doesn't work, we got to pivot and go to a different method.